Hello, class. Welcome to the second half of the course, Applied Mathematics for Industrial Engineering. Okay. Uh, as I mentioned to you in the Google Classroom before that, we already provide the link for the all the documentation of the detail that of the coverage. Okay. Of uh, all the information that you need for the final exam. Okay, so this clip of lecturing will explain, okay, through those documentation. Okay, as you see on your screen, this is the drive, okay, that I gave you, okay, through the Google Classroom. Okay, so you can access this. Okay, we're gonna start with the first slide here. Okay, um, I expect that you have a background of what we call ordinary differential equation, in the abbreviation we call ODE, okay, from your mathematics course last semester. Okay, especially in this form of what we call the linear differential equation, a sub 0 of x, okay, times y, okay, plus a sub 1 of x times first order of y, which corresponding to x, okay, plus a sub 2 x, okay, and second order differentiation of y with respect to x, okay, up to the n order, okay, a sub n, okay, of x, okay, times n order, okay, of y with corresponding to x, okay, and it's a differential equation with the equal sign here as the domain, the key domain of this equation is x, okay, and the resulting function that we are looking for is y. Okay, therefore the right hand side have to be arbitrary function, okay, depend on x, okay, where this is the definition of y, okay, superscript k, okay, with bracket, okay, this is the kth order, okay, of y uh, with respect to x, okay, when k start with, actually k can start with 0. 0 is a 0 order, so just no differentiation at all. Okay, 0, 1, 2, up to the n order. And also with this type of equation, we can write in general, okay, as a big function of x, okay, and with all the y 0 order, first order, second order, up to the n order, okay, and equal to 0. Equal to 0 mean that we move f of x here, okay, to the left hand side, okay, up. You look at the earlier equation that we discussed about, okay. This one we call the nth order, okay, differential equation, no linear, okay, because all these function can be have some nonlinear relationship, okay. So in mathematically, okay, we are looking for to find the y of x, okay, given the differential equation in this form, okay. Okay. Uh, since we I expect that you study some course on basic physics and also the mode mechanics and electrical circuit. Okay, so we're gonna apply this form, okay, of what we call the linear differential equation here with uh, some example. Okay, for example, this is the example we call the first order system, the first order equation. We look at this well-known the alternate circuits, okay, with electrical element of R and L. Okay, R is represent resistance. Okay, L is a parameter for inductance. Okay, and given the initial voltage, okay, E sub t, okay, and based on the Ohm's law, okay, we and IT, okay, happen with the closed circuit here, okay. From the Kirchhoff voltage law, okay, you can see that all the voltage within this loop, okay, have to be equal, okay. So based on the direction of the current and the direction of the voltage here, okay, so you can say that the voltage, okay, across this, okay, have to be equal to the given potential function here, et, okay. So as you know that by the Ohm's law, okay, the voltage drop across this load have to be IR, okay, V equal to IR, the voltage cross here. So it's I. And also with the given input of ET, E changing, okay, the amount of voltage changing over time, okay. So that result, okay, I have to be depend on parameter T also. Okay, so with ET change, okay, the voltage cross here, okay, I change over time also, okay, and times R as the voltage drop here. Plus, okay, as you know, okay, this is by physical law, okay, the voltage cross the inductance have to be L times di by dt, okay. So this is the voltage cross here, okay, across the inductance L, okay. So it have to be L di by dt, okay. So the voltage drop on R and both R and L with the direction of I, okay. This is additive, it's in additive form. So L di by dt plus R times it have to be equal to the voltage input cross these two poles, okay, et. Actually we didn't look at very complicated situation that R is a constant over for any t, okay, and L also is constant for any t. But if you look at in the general form here, okay, actually R for the linear differential equation, R can change over time and L can change over time also. Okay, but that's not what you study from the basic physics, okay. But in reality, okay, you can observe that when you have an equipment been using for a very long time, so how can you be sure that R can be the constant value? Okay, it may change, it can increase or decrease whatever the situation could be, the same as the parameter L here. Okay, but in this case we're gonna assume that L and R is constant. Okay, to solve the general form of this is a very easy example of linear differential equation. Okay, it's only the first order. We call the first order because this is the equation. Okay, you have differentiation term here, and the differentiation term here is only the first order term. Okay, so that's why we call this equation corresponding with first order system. Okay, and to solve this one, okay, we're gonna apply, okay, so this is we want to make sure that this is a review part of what you have studied, the technique of solving the ordinary differential equation from last semester. Okay, so in this one we start with trying to get what we call in many textbooks we call auxiliary equation, right? In the course, the mathematics course, we call auxiliary equation. But in engineering course, sometimes we call this equation characteristic equation. Okay, characteristic equation with L times S plus R equal to 0. Well, how do I get this equation? Okay, let's look at this equation. Okay, you just replacing uh, 0 the first order, okay, di by dt by S, okay, and with 0 order, okay, become S, this one become S with the power to the 1, okay, S1, oh, okay, S with the 1 power, okay, superscript 1, okay, S, okay, 1, okay, so if you have second order become S square, okay, if you have third order become S to the third, okay, S to, okay, but since this one is 0 order, it says S to the 0 is equal to 1. Okay, so this is a technique, okay, that mathematicians have already developed a well-established procedure for this. Okay, L times S is this one is S because it's a first order. Okay, plus R equal to 0. Why 0? Because we gonna assume that this is just the effects of on the system alone. Okay, with no contribution from the input ET here. Okay, and we're gonna find the root of this equation. Okay, why we call the root of this equation? Because if you have a higher order system, okay, this can be, you can have term of s square, s to the 3, s to the 4. Okay, so that's gonna, you have to find two or three more value here, but this one is only the first order, so there's only one root here. Okay, s, you're looking for the value of s. Okay, just move, okay, r to the right hand side, become minus r, and then divided l on both sides, so you get s equal minus r over l. Okay, this is the way we're gonna solve what we call the complementary solution. Okay, in engineering sense, we call this as a transient solution or transient state solution. Okay, and since R and L is a given constant value, so we can expect that S is a real number. So when the root of your characteristic equation is the real number, the general form of what we call ICT, we call the complementary solution here, ICT, equal to a constant, okay, time E, okay, to the minus R over L times T in this form. Okay, you can see that as you take a limit of T approaching the infinities, as you know that R and L cannot be a negative value. Okay, so you know that when you limit T approaching infinity, ICT is equal to 0. Okay, because this value keep approaching 0 value. Okay, that's why we call this a transient state. Transient state solution is mean that it's only happen temporary. Okay, as time goes by, okay, the system start to reaching what we call the steady state solution. Okay, but in mathematical term, we call this solution, we call complementary solution. Okay, the second part of the solution of okay, with this system is we call particular solution. In this case, we call steady state solution in engineering sense. Okay, IPT start to study the effect of the input ET to the system. Okay, but if you don't have a system here, okay, you might look at that when you have a ICT, okay, I sub CT is study the solution with no effect on the right hand side function. Okay, but IP sub PT is the general solution for IT. Okay, when you study the direct effect of the right hand side function. So the particular solution have to rely on what we call the structure, the type of ET gonna look like. Okay. Okay, so we move on that suppose, okay, we have ET equal to a general polynomial function order R. Okay, this is a sub 0 plus a sub 1 times t plus a sub 2 times t squared plus a sub t cube. Okay, t to the 4, t to the 5 up to a sub r t to the times t to the r. Okay, so if your input become polynomial function order R, okay, your corresponding output have to be this one also. Okay, so you can see that the form of IPT here, I sub PT here, will follow a similar form with the input, the right hand side function here, but with different parameter. Okay, you have same domain T. Okay, T is a domain, but the parameter of a sub 0, a sub 1, this is, since this is for the e sub t, e for the et. Okay, e as a function of t. Okay, so I sub p, okay, as a function of t. Okay, doesn't need to be a sub 0, a sub 1, a b sub 2, a sub r up to a sub r, just like et, because in the physical system, you know that et is a voltage, okay, it is a current. It's a two different value, okay, and different unit, okay. In physics, you got E have a volt, right? The unit count as a volt, and IT, okay, is the unit is the ampere, okay. So you know that since there are different unit, okay, therefore the parameter, okay, b sub 0 might be, okay, might not be the same, okay. It needs some transfer, some what we call relationship to find, okay. And the relationship to find that, what is the relationship to find between b sub 0, b sub 1, b sub 2 up to b sub r with a sub 0, a sub 1, a sub 2, sub a sub r to a sub r is, okay, considered by this differential equation, okay. So your idea is that, okay, you study what type of the right hand side function look like, okay. So particular solution, okay, will follow the same type of function as the right hand side, and then you put this form, okay, of IPT, okay, to the left hand side of the equation, and then, okay, start to comparing coefficients, okay, with the same term, okay, to find the relationship between the coefficients, okay, of the polynomial function of IPT, okay. So let's look at this, the equation that, okay, the left hand side you need to find the derivative, okay, of IT, okay, and you have IT here. So you need to find the first order of IPT, okay. So you put IPT, you're going to substitute IPT here, okay, in the left hand side of the equation. So you need to find the first order derivative, okay. The first order derivative here, okay, b sub 0, you find derivative of b sub 0 by dt is 0, because b sub 0 is a constant value, okay. For b sub 1, okay, with corresponding to t, when you find the first order derivative, become b sub 1, okay. This is a basic calculus here. With the second term, you find the first order derivative is become 2 times b sub 2 times t, and the third term b3 plus 3 to the 3, okay, become 3 times b sub 3 t to the 2, up to the r term, okay. Okay, you have r times b sub r t to the r minus 1 over here, okay. So now you're ready. Now you have, okay, first order of IP, okay, I sub pt, and the zero order of I sub pt you have formed. You substitute it to the left hand side here, okay. You see that the function, you have left hand side, you substitute it with ipt, okay. Okay, this L, okay, the constant value of inductance L time different first order derivative of ipt, which is this term, okay, you put it in here, plus r is over here, time ipt is over here, this one, you put it in here, and then you know that this left hand side have to be equal to the right hand side. The right hand side is et here, et have to be a0t. As you can see that you can have a coefficient comparison by, okay, this one is a zero order of t, okay, this one is the first term of polynomial function, the linear term, okay, with corresponding to t. This is a quadratic term, okay. You can have a cubic term, quartic term, quintic term, up to the r term here, okay. This one we're comparing coefficients on both sides of the equation. Before we move on, I want to make sure that this is all we apply what you have learned from the third course of mathematics from the previous semester, okay. But we just didn't go along with the just basic any kind of mathematical function. We're gonna use I will use two examples. One example is the electrical circuit. The second example is the basic mechanics, okay, mechanical system, as you will see in the next example. Okay, when you compare coefficient on both sides of the equation here, okay, let's look at the term that multiply by the constant term here. The left hand side constant term is L times B sub 1, okay, plus R times B sub 2, okay. This is a constant term, okay. No multiplication with any t, okay. And you can see the right hand side, the other parameter a sub 1, a sub 2 up to a sub r, all multiplied by t, t or t square up to t sub 1. Only a sub 0 is a term that no multiplication with t. Okay, actually times t to the 0, which is 0. Okay. So you can say that L times B sub 1 plus R times B sub 0 have to be equal to A sub 0. Okay. The second comparing coefficient is look at the term t here. Okay. The right hand side, okay, A sub 1, okay, times t. This is A sub 1 times. But the left hand side, the term that multiply to t is what? 2L, 2 times L times B sub 2. Oh, I will just skip B sub 2 here, okay. This the second term, okay, is R times B sub 1. R times B sub 1 here. So 2 times L times B sub 2 plus R times B sub 1 equal to A sub 1. Okay. Let's look at the quadratic term, okay. The coefficient that multiply quadratic term on the left hand side have to be 3 times L times B sub 3. 3 times L times B sub 3. Plus, okay, R times B sub 2. R times, R times, oh no. This is a mistake. It have to be B sub 2. Okay, sorry. This have to be B sub 2. Okay, R times B sub 2 equal to A sub 2. Okay, and move on. This is make sure that you correct this. Okay, this have to be B sub 2, not B sub 3. Okay, have to be B sub 2. This term keep going moving. You can start now see the trend L, 2 times L, 3 times L, up to the R term. Okay, the last term, R term. You have R, or no, before the last term, because the last term you can see that the first term, okay, you have all the coefficient up to t to the r minus 1. Okay, t power by r minus 1. Okay, so if you keep moving on here, okay, the first term here, okay, I'm sorry, this have to be b sub r minus 1. B sub r, correctly. Sorry. You can see that this keep moving on b sub 1, b sub 2, up to the r minus 1 term, which this one times t to the r minus 1. So the right hand side have to be a sub r minus 1. Okay, a sub r, the term before the last term. Okay, so this is the coefficient before the last term. Okay, so this one keep moving on from b L times 2L B sub 1, 2 times L B sub 2, up to R times L B sub R. Okay, plus, okay, this one R, always R here. Okay, the second term here, R, and start moving from B sub 0, okay, B sub 1, B sub 2. This one should be B sub 2. I make a, okay, that's why I make a mistake here. This one have to be B sub 2 and B sub 2, okay, and up to the t to the r minus 1, okay, which is b sub r minus 1. So this is a sub r minus 1. So this is comparing the coefficient here, okay, except the last term here. You can see the last term, okay, from the left hand side, okay, the first summation term, there's no 0 multiplication to t to the r, but only r times b sub r here. Okay, in the final, and the left hand side, r times b sub r here in the final, and the right hand side is a sub r. Okay, so you can see that you can find b sub r, okay, for the last term of b, for the order of a polynomial function here, b sub r equal to a sub r times divided by capital R. Okay, capital R is the resistant number. Okay, capital R here. So once you find B sub R here, you can do the back substitution. Okay, substitute back to find A sub R minus 1, A sub R minus 2, A sub R minus 3, up to A sub 2, A sub 1, and A sub 0. Okay, and that's what we did here. Okay, you can see that back substitution. Okay, we use this. Okay, we start to use the a sub r minus 1 here. Okay, a sub r minus 1 equal to r times b sub r minus 1, but this one rl times this one times b sub r, but you already know b sub r here is equal to a sub r divided by r. B sub r divided by r. So we substitute b sub r here by a sub r by divided by capital R. Okay, a sub r divided by capital R. So in this form, you can see that given a sub r minus 1, you already eliminate the term of b sub r because you found b sub r here. Okay, b sub r. So you just move this to the right hand side and then divided by r here. You get b sub r minus 1. Okay, so a sub r minus 1, move this term to the right hand side. Okay, so minus r times small r, okay, times L times a sub r small r divided by capital R. Okay, and all this term, put the bracket on this term, okay, because you want to divide all this everything that computed within this bracket, okay, by the capital R. Okay, and so on. Once you know b sub r minus 1, okay, you know b sub r minus 1, you can use from in the next equation, because the next equation going to look like this. A sub r minus 2 is equal to r, this one instead of r times L become r minus 1 times L b sub r minus 1 plus this one always constant. Okay, look at the trend of this term. Okay, this one is r, okay, times b sub r minus 2. Since this is b sub r minus 1 and this is b sub r, so the equation before become b sub r minus 1, this become b sub r minus 2. Okay, and then you can find b sub r minus 2 because you already know b sub r minus 1 by computing this. Okay, so you move it to the right hand side and then divide it, or put the bracket on it and then divide it by r. You leave the term b sub r minus 1, but you need to compute this equation first to find b sub r minus 1 and then put it in here, and then you get b sub r minus 2, and it keep rolling. Okay, you can, with this technique, okay, you can keep moving, okay, computing, okay, backward, okay, to get b sub r minus 1, b sub r minus 2, b sub r minus 3, up to b sub 0, okay, using this form. And once you establish this equation of b with related to a, remember that, okay, with this equation, okay, you given the input function of et, okay, e as a function of t, and you given the r and l as a parameter of the first order system. You want to find it, function which corresponding to t. Okay, and you know that to solve this, okay, you have two different type using the concept that you studied from last semester, that the solution of differential equation consists of two parts. First part we call complementary solution. This one you find the root of the characteristic equation, and then you get this form. Okay, but this one have to be ICT plus I sub CT plus I sub PT. Okay, you want to find particular solution, but particular solution you need to know what type of input look like. Okay, in this one we assume that it's a polynomial function order R. If it's polynomial function order R, you need to find using the coefficient comparison, so on both sides of equation, to find the relationship. Okay, once you know et, okay, as a function of t, so you know the value of a sub 0, a sub 1, a sub 2 to a sub r, but you don't know what the value of b sub 0, b sub 1 up to b sub r until you get this one first. Okay, you derive, okay, by balancing equation and comparing coefficients, okay, corresponding to each term of the polynomial function. Okay, you get b sub r, okay, first, and then you get b sub r minus 1, b sub r minus 2, up to b sub 2, b sub 1, b sub 0, okay, as a function of, okay, a sub r minus 1 up to a sub 1, a sub 0. Okay, and it become like a back substitution, okay, to get all this relationship. Once you know b, okay, we related to a, okay, you can establish what we call, this is the general function of the solution of I as a function of t equal to complementary solution plus particular solution, okay, which is equal to constant c. This is a complementary solution. C e minus r over L is the root of the characteristic equation, but since there's only one root here because it's a first order system, okay. Plus the second part is IPT, is a, you know, B0, B. You cannot write this, okay, just write it and answer it. It will be wrong if you cannot establish this relationship, that you can find b sub 0, b sub 1, b sub 2 up to b sub r for given a sub 0, a sub 1, a sub 2 up to a sub r. Okay, and that's the first, okay, example. Okay, and it's not over yet because let's go back and look at the equation first. Okay, here we still have, you already know, okay, find b sub 0 up to b sub r, but there's still one constant value still remain, is the capital C here. Okay, it is equal to I sub ct plus I sub pt. Okay, but it's almost finished, but this one is in general form, but you need to find what is the C value here, the capital C. The capital C value is you can find it if you can given the initial condition. Okay, for example, in this case, as you might familiar, okay, from the electrical engineering course or some physics course related to the circuit value, analysis of alternate current circuit. Okay, we would assume that, okay, I sub 0 is 0. No, I sub 0, I as a at time 0 is equal to 0. Okay, it's similar to the physical system like this, that okay, at time 0, okay, we close the circuit down, okay, to so that it become the complete circuit, okay, that can generate ET can generate IT here. Okay, so we assume that at the start there's no current, okay, but when you want to, okay, once the system start, you shut down okay, the closed circuit here, okay, by using this switch. Okay, so but within that few millisecond here, okay, the current change, okay, but from the start we give this initial condition I0 is equal to 0. So when you when you already establish IT here in general form here, you put t is equal to 0. Once t is equal to 0, you can see that b sub 1 times t plus b sub 2 times t square up to b sub r times t to the r are all 0. So the only remaining term here is these two terms. Okay, when t is equal to 0, this term become only c times 1, because these are e power to the 0. Okay, so it become 1. C times 1 is c plus e plus b0 is I0, but you have a 0 initial condition, so c plus b sub 0 is equal to 0. So you can find c, that c is equal to minus b0. You put this constant c, okay, to this equation. Okay, c is equal to minus b0, so b0 become the common multiplication term. Okay, you can put rearrange the term and get this general solution of IT. Okay, I keep type. Okay, now you can see that IT here, okay, is in the general form. Okay, It should be noted that in this example, okay, the domain of x is t. Okay, instead of x, we call the domain is t. Okay, and the range of y or response, okay, is it. Okay, this one just to compare with the original notation of ODE here over here. Okay, so this is and the physical system is lumped. This is the definition of what we call the lump system, is that R and L is a constant, okay, not varying with T. Okay, so that wraps up our first example to show you the application of using the technique to solve the ordinary differential equation to a first order system here. Okay, so we're going to move on to the next example here. This is a well-known example, okay, of we call the second order system here. This is according to the second law of Newton. Okay, you know that from the second law of Newton, okay, you know that F equal to F, the force, any force that apply to a constant value of mass, okay, they will generate what we call the displacement x of t. No, x as a function of t. Okay, and but the relation with for the force and the displacement xt here, function here, okay, can be follow the second law of Newton, that F is equal to m times acceleration. Okay, but the definition of acceleration is the second order of displacement with corresponding to t. Okay, so we just put this, okay, acceleration as the second order, okay, of x, a function of xt, okay, with the second order of t, okay, corresponding to the change of the domain, which is still the time domain here, okay, in the second order term. So with this equation, we basically what we call given ft, function ft, okay, but you can see now that you need two initial conditions. Okay, look back from the first order equation, you only need one initial condition because there's only one constant value, see here. Okay, from the complementary solution, there's only one constant that you need to find. Okay, but for the second order here, okay, you need two initial conditions. Why? Because with second order within the differential equation, you get two value of the root of the auxiliary equation or characteristic equation. So once you have two root, okay, your complementary solution will consist of two constant value that you need to find. So you need to have two initial condition here, x0 as a function at time 0, and the first order of x, okay, corresponding with time at time 0 also. So given two initial condition with the force function applying to a constant mass, okay, what is the function of the displacement? Okay, and also when times greater 0 is mean that when this force has been applied to the mass, okay, what is the displacement function gonna look like? Okay, this type of problem we normally call this what we call in ordinary differential equation, we call this initial value problem. Initial value problem is mean that you need to give an initial value, the condition, okay, sufficient amount of initial conditions so that you'll be able to derive a complete form of the output function or the solution function that you're looking for. Okay, if you considering within the finite horizon here, okay, for example, as t greater than 0, but if we finish it at some finite horizon period, capital T here, and after that, okay, f sub t becomes 0, okay, when t is greater than capital T here. It means that you apply the force function within the amount of time within t, capital T period, okay. In this case, okay, you given two condition also, but you didn't give the initial condition into just two initial conditions, just like the original question that I for the initial value. But this one we gave the starting function of the displacement x sub 0, x as a function t equal to 0, and the finishing displacement function at capital T, okay. So these two conditions here, okay, and you are the same as you have original equation, you have second order equation, but also you give these two conditions. You want to find the displacement function within this finite horizon. 3 is greater than 0 and 3 is less than capital T. In this case, we call this problem, we call boundary value problem. We call boundary value because we gave the condition at the start of the domain, at the toward and also at the end point of the domain, okay, and you only consider the response or the solution within that range of domain, okay. This one we call boundary value problem. But if you doesn't care, okay, how long t gonna be, okay, but you want to look at that it eventually, if the system makes sense themselves, it's going to reach some steady state solution, which means that there's only going to contain only IPT, the particular solution, or XPT. In this case, I is from previous example, okay. The displacement function of particular solution, because for the complementary solution, I already mentioned in the previous example, is that it's like a transient state. As domain T is approaching infinity, okay, the response will be approaching 0. The response of the complementary solution is approaching 0. Okay, so we're gonna look apply from the technique that you are using in the previous semester to analyze this problem. Okay, first, okay, suppose we're gonna suppose that, okay, m is equal to 1 unit, and ft function is the same as the et function from the electrical alternate current circuit from the previous example. Ft is a polynomial order r, and m is equal to 1. Okay, so in this case, f is equal to ft is equal to what? Second order of displacement function. Actually, when you multiply m, it start to convert the unit between displacement and the force. Okay, this one we suppose m is equal to 1. We are doing the same as that. If trying to balance this equation, okay, this one you need to find up to the second order. But at the same time, this is okay. If ft is equal to here, okay, so the equation gonna look like this. The second, since the mass is equal to 1, so the second order of x, okay, with corresponding to t, okay, is equal to ft, the function ft themselves. But xt, okay, consists of two parts from the basic solving procedure for ordinary differential equation. Okay, you have complementary solution and you have particular solution here. And the characteristic equation here, okay, you can see that since this is just a second order, there's no first order. Okay, so you just replace this second order with s squared. Okay, s squared here. Look at this, s squared. But there's no other term. You can look at from the first example here. Okay, the first example, okay, you have L. This is the first order. You have substitute the first order by s and zero order by 1. L s plus r. But in this one, we're gonna do this. Okay, here. But in this one, okay, since m is equal to 1, okay, for the this one, I have to be move this to the right hand side, okay. From look at this, as the right hand side become the force function. We assume to be polynomial function order r, okay. But this one is what second order, okay, of x function with corresponding to t, okay. So you replace this to find the characteristic equation, because this second order by s squared. But there's no other term from the left hand side here of this equation. So have to be equal to 0. But s, this is the quadratic equation, so there have to be two roots and it become the repeated root, okay. You know that s, they have to be equal to 0 on both root for the second quadratic equation here, s squared. Actually have plus 0 and minus 0, but plus 0 minus 0 is the same as 0 is 0, okay. So x complementary solution look like this. You can c sub 0 e, okay, to the s t. But since s is 0, okay, the e, the exponential term have no meaning because the power is 0, okay. So c0 e to the 0 become 1. But since it's a repeated root, okay, this is the technique from the last semester, the second term has to be plus c sub 1 times the domain. If it's a distinct root, okay, if a different value, so you can have c0 e to the, suppose s sub 1 and s sub 2, okay, this is s sub 1 and s sub 2. It can be c0 e to the s1 t, okay, plus c1 e to the s2 t, okay. But since it's a repeated root, the second term have to be c sub 1 times the domain is t, and time e to the s times t. But s is 0, so the second term become 1 because it's e power by 0 value. Okay, so this is a general solution for x sub ct. You can see that it doesn't look like transient situation like what we studied before, because if you keep taking the limit t approaching to infinity, this one is not vanish to 0. It's going to keep with the constant c sub 0 and ct. X sub ct is just keep accumulate. Actually, this problem is an unstable system. Okay, and if you study more on mechanics, you know that just you have a mass and you have force, it's not enough to control the stability of the displacement. Okay, you need more, like if you might remember, you might add a spring, okay, with constant k, okay, and you need to add a more element to the system so that the system will become more stable. More stable is mean that as t approaching to infinity, the transient solution vanish, okay. But in this one, you can see that it doesn't look stable at all. Okay, so we use in this case, okay, you know a complementary solution here already. Next, you need to find the particular solution. The particular solution, you look at the equation here. You have second order here, and then this one is what we call the right-hand side function. So we're gonna apply what we call the coefficient comparison, okay, by substituting the second order here by x sub pt. And you know that x sub p as a function of t, okay, have to follow what the force function look like. Since the force function is a polynomial order r, okay, polynomial order r, okay, but this one have to be followed, but it's not polynomial order r. X sub pt, okay, as a function will become the polynomial of order r plus 2. Any surprise? You might be surprised that what's happened. From the previous example, we still stuck with, okay, this is order R, IPT, order R. Okay, make a lot of sense. But for this one, for this example, okay, this one, the force function is the polynomial order R, but the resulting function that we are looking for from the differential equation, according to the relationship in the differential equation, it becomes order R plus 2. Why? I think that it makes sense if you look at the equation here. Since the equation here is at the second order here, okay, the left hand side second order of this one, equal to force function. Since the force function is polynomial order R, in order to make the left hand side resulting to be a similar function to the right hand side, you cannot have the order R here for the left hand side. Because if you have the order R here on the left hand side and you find the second order derivative, you're not going to be able to compare the coefficient from order t to the r and t to the r minus 1. You see the point? Because this one you find the derivative. Okay, the first derivative, okay, gonna reduce this polynomial function from order r to r minus 1. The second order will reduce from r minus 1 to r minus 2. And then the resulting function here from the left hand side doesn't have enough term to compare with the right hand side. Okay, so but why from the previous example it does work? Look at the previous example. Why this example it does work? You apply ET here, IPT, okay, it's the same order. Because you can see that it consists of zero order. Okay, the right hand side, the left hand side, okay, including the first order term and zero order term. Okay, so make sure that this similar function comparison can be used, okay, just in case only the left hand side have zero order term. If they have zero order term, okay, then the x sub p corresponding to t, okay, can follow the same order with the right hand side function. But in this one, since the left hand side you don't have any zero order, so you want, if you have first order, for example, just in case if you have first order on the left hand side, so the given function of xpt is only t to the r plus 1, because the first order term, once you find the first order, you still can keep some coefficient comparison with the term t to the r, because the first order term you need only t to the r plus 1. Since you find the first order, you still can have the term t to the r. Okay, so this is a little bit complicated, but it does make sense with the type of equation you're trying to apply here. So the same as we find the first order here and the second order based on the basic calculus term here. This is the zero order, okay, of xpt sub pt. This is the first order xpt. Okay, just derive this function. Okay, b sub 0 becomes 0 when we find, and this one becomes b sub 1. Okay, since the derivative, the first derivative of b sub 1 t is corresponding to t is only the constant bt, b1, b sub 1, the same as b sub 2 here. Okay, b sub 2 here, this one b sub 3 here. Okay, and so on. Okay, so with the first order, okay, you can see that the term reduced from the order r plus 2 to the r plus 1. And when you find the second order here, you can see that the term reduced it to only t to the r. And once you get t to the r, you are ready now to compare the coefficients between, okay, here, the last equation here with the original ft. Because you can see that this is what the equation look like here. Okay, so that's what this procedure do. Okay, so you can see that this one just make a comparison term by term. look at the ft here, and this is look at the second order of particular solution of x corresponding to t. 2 times b2 is constant value equal to a0. 3 times 2, okay, times b3, okay, b sub 3 equal to a sub 1. And 4 times 3 times b sub 4 equal to a sub 2. Okay, this one, keep going. Luckily, we don't need any back substitution. It can be comparing one by one. Okay. Actually, the first term is a sub 0 equal 2 times 1 times b sub 2. A sub 1 is 3 times 2 b sub 3. A sub 2 is equal to 4 times 3 times b sub 4. Okay. And you can see that the term, you can now see the general form, right? If you keep adding up to r minus 2, okay, this one start from 2, 3, 4, okay, it lead this sub by just 2 units. So this one is r minus 2, it become r times r minus 1. Okay, this r have to be greater than r minus 2 by 2 units, and this one reduce it from this term by one unit. Okay, and when you move to r minus 1, become r plus r change to r plus 1, r minus 1 change to r, and when the term of ar it become r plus 2 and r plus 1. Okay, therefore you can find b sub 2, b sub 3, b sub 4 up to br sub r plus 2 with given a sub 0, a sub 1, a sub 2 up to a sub r. Okay, here. Okay, I just keep making a mistake of pushing the button. Okay, you might wonder that this start from b sub 2, b sub 3, b sub 4 up to b sub r plus 2. But what is b sub 0 and b sub 1? What's happened? You can see that the term is b sub 0, b sub 1, b sub 2. You know that, okay, you can find the relationship from b sub 2 up to b sub r plus 2, okay, here, okay, for given a sub 0 up to a sub r. So b sub 0 and b sub 1 become arbitrary. Arbitrary means can be any value. It doesn't matter because it's included in the zero order and the first order term. Once you found the second order, this term is vanished. So it doesn't matter how b sub 0 and b1 gonna look like. Doesn't matter, because based on the governing law, okay, of physics leading to the second order system, this value have no meaning. Okay, so it can be set up to any value. Okay, so you can now conclude that, okay, xt function is a complementary solution plus particular solution. Okay, this is the complementary solution, c0 plus c1 times t, this one. Particular solution is here, okay, plus, okay, b0 plus b1t. Okay, you can see that these two terms, okay, actually, since b0, b sub 1 can be anything, okay, so you just can move these two terms, okay, collectively, combining these two terms to become c sub 0 becomes c sub 0 star becomes c sub 0 plus b sub 0, and c sub 1 star becomes c sub 1 plus b sub 1, and combine these two terms, okay, to be an integrated part here. And this one is, since it's very easy to substitute, I just substitute b sub 0, b sub 2, b sub 3, b sub 4 up to b sub r for given a sub 0, a sub 1 up to a sub r. Okay, so this is a general form of x sub t. But again, you still need to find c0 star and c sub 1 star here, because you combine these two terms together. C sub 0 star plus C sub 1 star here. Okay, because since you know force function, okay, so you know the value a sub 0, a sub 1 up to a sub r. But now the remaining term is all clear, but still not clear what is C0 star and C sub 1 star. That's when you need what we call, okay, two initial conditions here. Okay, suppose you have I just gonna be very briefly that suppose that x sub 0 and x pi sub 0 is equal to 0. Okay, for any given value, okay, since once you find t is equal to 0, okay, you can look at here that this is the xct, okay, the complementary solution. When t is equal to 0, okay, become c0 star. But when you find the first derivative, okay, the first derivative, this term is vanished. Only c sub 1 star remain. And once you try t is equal to 0, certainly all this term gonna be vanished because it's have the up to the quadratic term, the cubic term, and once you only find the first order, okay, the term t not gonna be vanished. So it can be easily concluded that for given x0 and the first order, okay, condition at time is equal to 0, so it's no matter this value is, this is the resulting of c0 star and c1 star, okay, for given initial condition. And for boundary condition, okay, instead of I give you given x0, okay, and xt at a finite horizon t, okay, so x0 is the same, t is equal to c0 star, but x at t, okay, it become more complicated because you have to look at the whole function, because now you're not substituting t, small t by 0 anymore. You're substituting the small t by the capital T. So when you combine with this capital T, okay, you need to make sure that and this is not condition with any derivative form. So you need to use the direct x t function that you derive here. So when small t is equal to capital T, okay, x of t here, okay, so you just put it here. It's gonna be c0 star plus c1 star times t, and then all the remaining term, okay, a0 divided by 2, a1 divided by t times 2, and all of this, okay, at t. Substitute small t by capital 3 up to order r plus 2, okay. So this one you for x0, okay, the first condition you'll be able to find c0 star. So c0 star you already find from the first condition, but to find the c1 star, okay, to find the c1 star, okay, you need to move, okay, this to the left hand side, x sub t minus c0 star, and all the remaining term except c1 star t here, the remaining term to the other side, okay. So xt minus all of this, and all of this, okay, since the term c1 star, okay, is time t, so if you divided all the term that you move to the other side by t, so you get the result of c sub 1 star here, okay. So this is just a start, okay, that to review, okay, let's say that we review, it is in a reviewing part, okay, of applying the knowledge that you study from the third engineering mathematics course from last semester, okay, to solve a basic engineering physics problem, one for the alternate current circuit, and the second example is the second law of motion according to Newton's, okay. And also we introduce you the concept of what we call the initial condition and the boundary condition in order to complete the derivation of the solution of the differential equation, okay. And in the next example, okay, we're gonna apply in a more complicated situation, like circuit system become the second order, okay, and we're going to have some more example to illustrate to you in the next clip, okay. From the start here, this is a clip number 1, okay. I'm going to stop here, and then, okay, so you to take a rest, okay, or review watching back, okay, move since this clip will be posted on YouTube, you can, if you don't understand anything, you can move back and re-listen to it again, okay. Okay, so in the next clip we will start with the document number 10, okay. So for this one, okay, we're gonna stop here, okay.